I don't know.
No, I mean like.
I know what you're talking about. I don't know what day it is.
Mickey, what day is it?
Today's the 29th.
Thank you,
Okay, so we're going to do a little bit of geometry today. We're going to do a little bit of algebra. We're going to combine those two things into making the calculus fairly understandable. And I know that some of you who are currently enrolled or have already had physics, you may have delved into some derivatives already. However, the process that they show you in physics is a little bit different than what we're going to use in here, and we use a little bit more of a build-up to it instead of, because you need to understand how it works and where it comes from more so in here than you do in there where you just need a mechanical application. Okay, so you should be able to understand the difference between tangents and secants. So again, a little bit of geometry going on there. You need to be able to find the slope. Hopefully that's not a big deal. You can all do slopes, right? No? Okay, I understand. You're not going to like the using the limit definition for the derivative because you've done that before and you've already expressed a displeasure with it. You know what this is, right? This is the as delta x approaches 0 of f of x plus, yeah, we'll get to that. Again, you're not going to like it. And then you're going to need to understand the relationship between differentiability and continuity. Okay, so this is the ability to differentiate a function. You already know what continuity is, the ability to be continuous. And they have a relationship which we'll get to later. Okay. I'm sorry, what? I don't know. I mean, how could I answer that question? Did you cry in the movie Up?
Yes.
Okay.
Who didn't cry in the movie Up?
You heartless sons of...
It's a good movie, I just think.
You didn't cry in the beginning of Up.
You cried.
Just like admit
I
it.
was.
I wasn't even crying. I was like,
It was.
You have just a cavity in the center of your chest. Are you the guy that's like sucking on his Diet Coke or Coke and people are just bawling uncontrollably and you're munching popcorn while people are having a...
Well, I fired it.
So you weren't in the theater.
You guys seen it?
I'm sorry, what?
You seen it below?
Eight Below.
A bunch of dogs get killed.
Yeah, that just took a right turn right into the rest area there. Anyways, thanks for causing this. You should work on this.
I might.
Good. Okay, so tangent line versus secant line. Tangent line will intersect the function in exactly one spot. The second line is important. We are done, for the most part, talking about points on a function being the point x, y. We're now going to refer to those points as x, comma, f of x. Even though f of x is the same thing as y, it's time to treat this like big people here. And so points will be f, comma, f of x. That's also a very helpful concept to remember when we're doing certain problems. To in the future. Secant line passes through a function in more than one point. Could hit twice, could hit a gabillion times. Secant line, no limit to how many times it hits as long as it's more than one. Tangent line, only once. Okay, we good? What's the P? P stands for some point, P. I just called it P. P for point, P for Puma. Pentagon. What'd you say? Panda, penguin.
Polar bear.
Polar bear, good. Well, that's,
It's 2 words.
is that a P or is that a B?
Oh.
It is a bear.
It's like peanut butter, you know. It's 2 words.
We're gonna get into this again.
Peanut butter and
Peanut butter.
Butter.
Peanut butter
Peanut butter and
butter.
butter.
Same thing,
Did you
right?
say peanut butter and butter?
That was my
This man.
It's as bad as like peanut butter and mayo.
Okay, mayo's gross enough on its own.
Yeah, I don't eat that.
Yeah, something like that.
That's as bad as like peanut butter and mayo.
Why would you even put those two things together?
Because he said peanut butter
That
and butter.
consistency
He doesn't
in
eat
your
that.
mouth
He doesn't
is
eat
just-
that.
I don't hear the same.
Oh, does anybody eat peanut butter and mayo?
Someone's gonna try it now.
No, you are not.
I'm not.
Okay.
Just like, it's gonna spark some ideas for other people. Why?
Whoops.
You like mayo. This is your regret it. It's really regret it.
No. Oh, gross.
No.
It's gross. Okay.
I don't think so.
Okay, so here we go. Let's look at a little bit of geometry here. So, this will be fun. I've got some function, and this picture is the blue curve. Oh, it might be a cubic, it might be something bizarre, who knows? But it's a function, which I've called f of x. And I've got two lines there. I've got the red line, which represents a tangent because it hits in only one spot, P. And I have a secant line, which is the bright green. It hits in 3 spots. And again, we don't care how many it hits as long as it hits in more than one. What I want you to see first is the notation that I'm using for this point, or for this picture. So notice that the point P is at the location x, comma, f of x. Again, we're ditching the y terminology and using f of x now. Then I've got this point Q over here. So how did I get to Q? I took P and I shifted over some distance. That distance is called delta x. Delta means change, so it's a change in x. I happen to move it to the positive direction. It doesn't have to go positive, it could be negative, but that works just dandy for me. So you'll notice now that the coordinate of Q, the x coordinate of Q is x plus delta x. That looks familiar, doesn't it? Yeah. So what's the y coordinate of Q? One person, please. Thank you. F of x plus delta x. Now, the question is, what happens when Q moves closer to P? I'm sorry? Chaos ensues, yes. Luke?
If delta x becomes smaller,
Ooh, how small, Luke?
well, if Q moves, let's say, 2 units to the left, then delta x will become 2 units smaller.
And as we continue to move Q closer to P, what happens to delta x, Luke?
It would keep getting smaller.
Uh-huh. And what would eventually get closer to? Well, hold on, let me interrupt for a second. Let me interrupt myself for a second.
Okay.
Can you interrupt yourself? Never mind. What do we call that when something gets closer and closer to another value?
A limit, like a limit.
Thank you, Luke. A limit. Good. You really want to be called limit, Luke? I mean, I can make it happen, but okay, good. So we call it a limit, right? As delta x approaches what in this case, Luke?
X or P or negative. What is that?
Nope.
No.
Let me ask my question again and don't look at the picture.
Okay.
What do we want delta x to go to?
0.
Bingo. Okay. So it doesn't matter where x is, the difference between P and Q is going to get smaller and smaller and smaller until delta x approaches 0, which is a limit. And so you start to realize what's going on here. What's the slope of the line PQ? Hold on, let me write some stuff we've said already so the visual learners in the crowd can. Okay, we put this point at x comma f of x. And Olivia, tell me again, where's Q?
F of x plus delta x.
Okay, so x plus delta x is the x coordinate, comma, f of x plus delta x. Outstanding. So the question is, what's the slope of PQ?
Wait, why is it f of x plus delta x?
That's the y value you get.
That's the y value you get when you plug x plus delta x into the function. Hey, Tom.
I'm just curious, are we no longer using numbers? We're just
I understand. It would be nice if I just said, well, x is at -1 and delta x is 3, so we're over at 2, and then we go from there. That would be way too easy. What we're doing is establishing the process of where this thing called differentiation comes from, and then we'll start plugging in numbers. What do you got?
Are we, for the, on the left side for x comma f of x, are we specifying which line that's for, or is that just the whole intersection?
That's for P.
That's, okay.
Okay, so there's this one is the coordinate for P, this is the coordinate for Q, and again, my question is, what's the slope of PQ, Mason?
F x plus delta x minus f of x over x plus delta x minus x.
You with me so far? X minus x goes away, and look what we have left. F of x plus delta x minus f of x all over delta x. That should look familiar, yes? This is where people start to cry.
Okay, so yeah.
So getting back to what you were telling us, Luke, now if I want to move Q towards P, what do I need to do with that puppy?
You need to get the delta x out of the denominator.
And how do I do that?
You could multiply by.
Oh, I'm sorry, you're talking about the mechanics of doing that? Yeah, we'll worry about that later.
Oh, okay.
Okay, but what did we establish? What happens, what do we want delta x to go to?
0.
0. And how do we express that?
With a limit.
Beautiful. Question.
Before you cross those two out, was that x plus delta x minus x?
That was x plus delta x minus x.
Okay.
Right. So that was the x2 minus the x1 from the slope. Okay? So you see what we're doing here. We're eventually going to take Q and move it over to P. I don't have enough information to find the slope of P. I only have 1 point on it. But I want to find the slope of P for a variety of reasons, which we'll talk about later. In order to find the slope of P, we're going to cheat by taking a secant line and turning that secant line into a tangent line. Can I erase this? Yeah. Good. All right, let's go back to the slideshow then. And we'll come back to this picture in a second. Okay, we answered that already. There's the picture again. We did that. We did that. We got this. We're good. Okay, so that's exactly what we've already done. So we're good to go so far. And then we answered that question already. Luke helped us out with that, and we're getting to this. Okay, so now watch what happens. It does all kinds of craziness. It intersects the graph in a whole bunch of different points. It slows down there for some reason. But eventually, you're seeing delta x is getting smaller and smaller and smaller, which we represent as a limit. So we're shrinking delta x till eventually Q will fall right on top of P, where delta x goes to 0, and in fact it disappears. Boom. Okay? So how do we do that mathematically? We do that by shrinking delta x down to 0, which is the same thing as taking the limit. So if I want to know the slope of this red line, I'm going to find the slope of that red line by using a limit. Okay? Is the concept there? You following me? Okay, now let's talk about the mechanics. Did that, we did that, it's a limit, great, there it is. So the slope of that red line, which is also a tangent line, is going to be found by using that puppy, which is the difference quotient with a limit stuck in front of it. And this is why we've been playing with this difference quotient a little bit in the class now, is that instead of seeing it for the first time here, if you work with it a little bit earlier on, it makes this transition easier. Okay, so if I get rid of the limit portion of that equation, I have the slope of the secant line. That was the green one. If I put the limit in front of it, then I have the slope of the tangent line, which was the red one from the picture. Make sense? Okay. Everybody good? All right. So, let's do it. We want to find the slope of the tangent line at the point 440. And then use that to find the equation of the tangent line. So, simple question. What are the two things you need for the equation of a line? Slope and a point, very good. So we're gonna start with the slope. We already have the point, and we'll go from there. Okay, here we go. Okay, so we're gonna find the slope by doing the limit as delta x approaches 0 of this. So that would be 3 times x plus delta x quantity squared minus 2 times x plus delta x squared, not squared, just that, minus parentheses 3x squared minus 2x close parentheses all over delta x.
Is this A?
This is A, yeah, finding the slope. These parentheses on the back end are very important. You have to be sure to put those in every time or you're going to make some sign mistakes. The other thing that people don't like is you have to write the limit every time. Let's see, that would be 3x squared plus 6x delta x plus 3 delta x squared minus 2x minus 2 delta x minus 3x squared plus 2x all over delta x. Come on, who's having fun? Just go ahead, just throw it there. Thanks, Max. A couple brownie points never hurts, Max. Good job. Okay, what do we got? We got a 2x canceling with a negative 2x. That's good. We've got a 3x squared with an x squared, 3x squared canceling. So we get the limit as delta x approaches 0. Okay, so these all have delta x's in them, so I'm going to skip a step here and factor out a delta x. Okay, what's the limit? Nope. As delta x goes to 0, what's going to happen to that middle term? Goes to 0. What happens to the 6x? Nothing. What happens to the negative 2? Nothing. Now, some of you might know the easier way to do a derivative, but again, we're not there yet.
Wait, why did the change it back to?
Because we took the limit then as delta x went to 0.
Oh, okay.
Now, this is the part that freaks people out. You are used to finding a slope and getting a numerical value. The slope of that line is negative 2. The slope of that line is 1, etc., etc. This is a slope. But the slope changes depending on where you are in the graph. So if you think about that Sketchpad demo I showed you, the red line was over here. If I move that red line, the slope is going to change. This takes into account anywhere on the graph what the slope will be. Does that make sense? And that's a really important point. People get frustrated when they calculate a slope and they don't get a numerical value. The slope changes depending on where you're talking about on the graph. Where are we talking about on the graph? 440. Which means that the slope at 440 would be 22. Does that make sense? If I move the point, if I take a different x value, the slope will change. Again, think about that red line going along the curve. Its slope would change depending on where you're at. I'm choosing to put it at 440. So what's the answer to B?
It's 1 over 22.
Say what?
Negative 1 over.
Where did the negative 1 come from?
Isn't it like
Oh.
No.
Y minus. Oh. Okay.
Lucas.
Y minus 40 equals 22 times x minus 4.
Perfect. And again, leave it in point slope form. Don't simplify it. Let's stop for a second, make sure everybody's with me. Are you okay? There's two parts to that that you need to be concerned about. One is the concept and understanding what's going on here. The second one is the mechanical stuff. The mechanical stuff, I'm thinking at this point, is probably the easier of the two, but I might be wrong. Doing this stuff. Because you've been doing limits for the last chapter. This should be okay. It's understanding why we're doing it and where it's coming from, which is more important.
I have a question about part B.
Yep.
So, would you use the numerical slope or?
Yes.
Okay.
Yeah. Because we know where the point is, you can plug in the values to find the numerical slope. If they didn't give you a point, then it gets into a weird problem because now everything becomes like theoretical. So you'd have like y minus y1 equals that business over again. We'll have it at a certain point. Okay, get rid of that. Come over here and let's see. Dun, dun, dun. Oh, look, I already did it. Okay. Yeah. Yeah. Oh, why did I do all this work? 22. Beautiful. Yep. Yep. Good. So we got the right answer. Everybody's happy. Quick video.
That's awesome.
It's one of my favorites. And have a nice day. Oh, isn't that horrible? Unbelievable.
That's awesome.
Yeah. Want to see it again?
Yeah.
Thought you might.
What happened to her? Like, is she okay?
She's fine. She was actually on Jimmy Kimmel one night.
Really?
Yep. She got really lucky though because she had it looked like she had a glass in her hand that she set down. Pretty
Where
horrible.
was it?
I don't know.
The gas station? Where was the guy?
Office.
I think it's a bar or something because it looks like she's pouring a beer, and then the two chuckleheads who walk by and don't even bother telling her there's a giant hole in the floor. And then the woman, she probably killed the woman downstairs. The one that goes down ahead of her, she probably landed on her. See, she looks like she's pouring beer, and she has it in her hand, and then she sets it down, thankfully. And then these two idiots don't go, oh, by the way, there's a hole behind you, and then she just
Looks like a pretty long
They
fall
didn't even
too.
look that shocked when she
What's down?
Yeah, they're probably like this.
Oh,
every other
yeah.
color.
Boom goes down like.
One more time.
one more time. All right, one more time. One more time.
Watch their reaction.
Watch her hands when she falls. That's the most horrific part.
I named her Sharon the bar.
You know she broke it in.
Which
But Zingo.
I saw like boom goes down.
Crazy.
do you know how terrifying that would be? You take a step back and you're just like falling.
Yeah, there's nothing you can do about it. It's horrible. Okay, so this is a an alternate form of the thing that we've already done. And so we start with something simple like the limit is another way to refer to the slope is delta y over delta x. That's fine. But this is another way that you can refer to it where c is some point. So now we take a value at a starting point. Instead of just x, we know where we're starting at. So I forget who was saying it, but you were trying to tell me that x is at, -1 something or another, somewhere around there. This will allow you to do that. It's just a variation. It's not one we're going to use a lot, but it is something that you should understand. And again, notice the notation. At the point c, you'd have c comma f of c, where c is some number. So instead of working with variables there, we would be able to work with specific numbers. Okay, got it?
Was that in the book too?
Sure. Find the slope of the graph of f of x equals 2x minus 3 at the point 2, 1. We just did this type of problem. I simplified the function. You do this one now. Set up your equation carefully. Multiply everything out accurately. Cancel. Get your answer.
Where are we supposed to use that?
I'm sorry?
Are we supposed to use that?
Formula?
That we.
Yep. That formula, by the way, is what's called the formal definition of derivatives.
Wait, the formula you just gave us, or the one that?
The previous one, limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta. That one. Okay, stop a second. Before you get angry with me, let's think about this. So let's talk about some concepts here. What can you tell me about that function? It's a line. And what are we, shh, don't spoil my fun. What are we doing with this problem? We're trying to find the slope of the tangent to a line. If I pick any point on that line, what's the slope going to be of the tangent to that line?
Same.
Nope. Same as the line. Okay? So what's the slope of the tangent to that line? 2. Good. Now, if you were working fastly, whatever, if you worked quickly, you might have been able to plug that in and simplify it. But if you use your brain a little bit, you realize you don't have to do that. Any point on that graph, the slope of the tangent line is going to be the slope of the line. That's not true in the previous example we did. With that parabola, it's going to change as you travel along the parabola. So therefore, this becomes a fairly simple problem. The slope is 2. The point is 2, 1. You're done. Okay. Go ahead.
I'm a little bit confused on the slope. Tangent lines are perpendicular or not?
Nothing. Yeah, they're just intersecting in only one point.
Oh, okay.
There are certain instances where we can talk about tangents or perpendicular and stuff, but we're not ready to go there yet. Okay. So yeah, that's what I talked about. Okay.
I don't get it. Wait, how do you? So you don't do any other thing we did for the last problem?
I'll draw you a picture.
Okay.
Okay. So let's suppose my function looked like that. Okay. And I bring a tangent line in there. Depending on where I draw the tangent line will affect the slope of the tangent line. Right? So if I do this, I'm going to have a slope like that. If I come over here, I'll have a slope like this. If I come over here, I have a slope like that. Okay? So if I calculate the slope of that function, if I calculate the slope of the tangent line to that function, I'm going to get an equation because it changes all the time. You good with that? This is a weird instance. Here's my line. Or I should say, there's my function. Well, what's a tangent line look to this function? Well, let's pick this point right here. Oh, the tangent line is going to be the same as the line. Draw a tangent line here. Same thing here. It doesn't change. It's always the same as the slope of the line.
Can't you go like that then?
Like this,
Like where yeah.
it wouldn't be tangent.
Isn't that
Or
only
is it a totally different line?
It would be nothing. It'd just be an intersecting. Something like that would just be an intersecting line. It's nothing.
Oh, okay.
Got it.
If it's like that, though, it has the same slope, should one of these intersecting more than once?
That's a good point. Yeah, it kind of defies the definition of tangent because that tangent line actually intersects the line in more than one point. We just kind of ignore that and pretend it does. This one?
Yeah, if you would continue it.
Oh, I see what if you continue it? Yeah, but we're focusing on, again,
Just at that point.
where we talk about small quantities in calculus would be the case. I understand the line goes on forever and it would hit in more than one spot, but for our purposes there, we're looking at the small area around that
You're
point.
looking at the singular point. more
You
than
got it.
just-
Yep. Yep. Go ahead.
Wait, so how did you find the slope for this one then?
Just took the slope of the line. Okay. Alrighty then. Alright, what if we have a vertical tangent line? So first of all, understanding what a vertical tangent line is. Well, what if I take that tangent line and I move it around that curve till it reaches a point where it's pointing straight up and down? Things get weird because what do you know about the slope of a vertical line? It's undefined. So we can't really plug into the formula because we'll get all kinds of weirdness. So we're going to use this guy. If this formula gives you infinity or negative infinity, then you have what's called a vertical tangent. So think about that tangent line sliding along the curve, and it comes over and eventually keeps going down and down and down until it becomes vertical. Its tangent is going to get bigger and bigger, its slope is going to get bigger and bigger and bigger until eventually it gets so big, it's infinity. And either one of those works. If you do the calculation, you get infinity for the limit, or you do the calculation, you get negative infinity for the limit. That's going to imply that you have a vertical tangent line. They're not incredibly common, but they do pop up every once in a while. 10 after? We're fine.
So it's just the same thing, but when you have infinity as the answer?
Yep. That means your tangent line is going to be going straight up and down. We're not going to focus on this more. We're actually going to do the opposite. We will spend an exorbitant amount of time looking for where is the tangent line horizontal. We care about that more. In other words, when is the slope equal to 0? That has bigger applications for us than this business. But you still need to understand why and when this pops up. Okay? Vertical tangent line, graph out. Okay, beautiful. There's a picture one. So again, it's a continuous curve. Nothing funky happens. It's just doing its thing. But again, if you imagine that tangent line is coming in here, it's getting bigger and bigger and bigger and bigger and bigger until it hits an undefined value, and then it starts to curve back over. So they do pop up.
That doesn't count though?
I'm sorry?
Didn't you just say that doesn't count, goes through it?
This?
Isn't that just an intersection?
Well, but again, we're looking at small little points here. So we're looking at a slope in that little area here. And then as that point continues to move, it changes, and that's going to cause some problems because it's flipping from one to the other. So it's going from this way to that way. That has a name, which again we'll cover. That's a special point, which we'll get to, and I don't want to confuse anybody yet. Okay, so now we talk about the derivative. So all of this business that we've done so far is we've addressed this graphical idea of what is a derivative. And for our discussion purposes so far, we've defined the derivative as the slope of the tangent line. That limit function. Limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay. Now we got some new notation and some new terminology. So we're taking a derivative, which is also known as differentiation. And we have some new notation right there. And that's read as f prime of x is a way to represent the derivative of a function. This, they call it the definition of the derivative. We're going to call that the formal definition of the derivative because we're going to learn a bunch of tricks that make our life easier. But of course, we're going to continue to come back to the formal definition of derivatives. So when it says formal definition of derivatives, you're going to be using this limit formula. Okay. As I said, that's read as f prime of x. It's just another way to denote a derivative. And we're going to talk about f prime of x, f double prime of x, f triple prime. We'll just keep taking derivatives over and over again. All of these things mean the exact same thing. They're just different ways to write the same thing. Most commonly, we'll use the first two, f prime of x and dy dx. Occasionally, you'll see these other things pop up. Not very often. The second one, dy dx, is important because it's just a different way of talking about it. F prime of x means you take f and you take the derivative of it. Dy dx means you take the derivative of y with respect to x. And that with respect to x thing becomes relevant later on. Initially, it's not a big deal. We're always going to take the derivative with respect to x, but that will change later on when the problems get nastier. Okay. Again, different ways to say the same thing. So I feel like I'm beating a dead horse here. Okay, that's Isaac Newton. That's Leibniz. Check out the hair on that dude. So, two guys both create calculus at the same time in different locations. Newton, I believe Newton was British and Leibniz is German or Austrian, I'm not sure. So, anybody know anything about Isaac Newton? What do you know about them? Everything? Like what?
Wow.
Reaction is an equal or opposite
His
reaction.
father was a blacksmith or something, he did a favor for some sort of lord who paid for his education.
You know anything about his personality? Major jagbag. Isaac Newton was a complete and utter nasty person. But he was pretty bright. So, you know, we hear the story about the apple hitting him on the head and he did discover gravity. It was there all along. Leibniz is like the underdog. He's this little guy who's mathematician. He wants to be famous like Newton, but he's just doing his thing. They come up with calculus at the same time. Newton thinks there's no way this guy came up with the same ideas that I came up with because I'm Isaac Newton. And at the time, Isaac Newton was in charge of some big physics/math community. So back then, mathematicians were like rock stars. So Newton was a household name. Everybody knew him, signed autographs on the street, that kind of thing. He hears about Leibniz and ruins his life. Just completely destroys, goes after him, accuses him of plagiarizing, a whole bunch of other things, just makes his life a living hell. Leibniz ends up dying, broke, poor, destitute. Newton goes on to be Isaac Newton. Everybody knows Newton. No one knows Leibniz. It's a sad story. What you saw in the notation are the two different forms that each of them used. So, I think I got it on the next slide. Yeah, why won't it go? Click. I guess I'm not ready to rumble, right? There we go. Okay, no, sorry, I went to go, now we're going to go back again. Okay. The different notations, these two notations came from each of those guys. This one is Newton. I'm pretty sure that one's Newton. That one's Leibniz. They used a different notation to do the exact same thing. They really don't know, they being historians, don't know what happened. The odds of both these two guys coming up with the same ideas of concepts is pretty slim. But the question is, if they didn't, who copied off of which? Did Leibniz actually have access to Newton's notes? No way. Did Newton know enough people that he could steal Leibniz's idea? Who knows? They just, so that what they've kind of done is just said, okay, they both created calculus. Which is a cop-out, but now we have to wait again. Why isn't this going? There we go. Okay, so we want to find the derivative of that. It's the exact same problem we just did. We're going to use the limit formula to calculate that derivative. And it gets nasty. So don't write, just watch. Because you don't want to multiply out a cubic, do you? No, good. Notice the notation. F prime of x is equal to the limit as delta x approaches 0 of all that other business. That's purely the definition of derivatives. Later on, we're going to throw that limit idea away and look at some other techniques. That's where things are going to get nasty. We're going to put the concept away and get into the mechanical part. And it will get more difficult because you'll have a lot of different ways to take derivatives. This one, I didn't even go through it, but you can see how difficult that would be. What do we have to do with the cube thing? So let's set this up. We won't do the calculation because it is a little nasty. What would this derivative be? F prime of x would be the limit as delta x approaches 0 of x plus delta x quantity cubed plus 2 times x plus delta x minus parentheses, very important. Okay, good. So there's the setup. The rest of it's nasty. You got to multiply out the cubic, and whether you use Pascal's triangle or you just grind it out, whatever you want to do there. Things will cancel out, and you'll end up with a nice, pretty answer. Question? You can't wait 9 minutes? No? Okay, go ahead. Should we wait for you?
If you guys want.
Oh, it's up to you.
I don't know.
You don't want to? Okay, never mind. Take the passage. So multiply that out. When everything is said and done, you will end up with 3x squared plus 2. And that's somewhat the frustrating thing about this is you got this big honking formula, with a big monstrous numerator, and when everything is canceled out and you take the limit, you end up with something nice and pretty. And now we start to compare differentiability and continuity. Another form of the derivative. And so what that's saying is, instead of taking a derivative anywhere on the graph, I want to look at a specific point C. The reason we have this form is pretty much to deal with derivatives of one, maybe two functions. In particular, we'll use this for absolute value graphs, because it's not an easy calculation without this. So I get something like that. It's the exact same picture we talked about before, except we're starting at C and moving over to X. And like I said, we would use that for the absolute value graph. So I've got this graph that's the absolute value of X minus 2, and it's continuous at 2. Are we all in agreement? Okay, no problems there. There's no holes, there's no jumps, there's no asymptotes. What's a derivative at 2? Okay, while you're thinking about that, what's a derivative at 1? -1, because it's the slope of that line right there. What's the derivative at 3? 1. Any problems there? Good. What about 2? 0 would be a good guess. Does not exist? Why? Is that you, Claire Dyer? Yeah.
Because there's no like line, it's just like a point, so like there's no slope defined.
So you're saying my tangent line doesn't have to look like that? Could it look like this?
Yeah.
It could look like this?
Yeah.
It could do a whole bunch of different things. So you're just going to say does not exist?
Say both. All reals, which means -1 and 1.
-1 and 1. So a lot of options. The answer is it doesn't have a derivative there. That's what's called the corner of a graph. When a function comes together into a corner where it's not apparent where that tangent line would be, you get what's called a corner, and it's non-differentiable at that point. Okay. But still continuous. So notice continuity in this case did not determine differentiability. We did this already. If you come from one, no, we didn't do this already, sorry, that's wrong numbers. If I do the limit coming from the left-hand side, we get a value of -1. You told me that already. If I come from the right-hand side, I get a limit of 1. And when the left-hand side doesn't match the right-hand side, what do you know about the limit at that point? Does not exist. And since we've defined the derivative as being a limit, it therefore does not have a derivative at that point.
But doesn't it still have a limit?
No.
Why doesn't it go? If you go back. Why isn't that? Isn't it double approaching 0?
The limit, yes, to answer your question, the function has a limit. But remember, we're not talking about the function, we're talking about this guy. We're doing this limit, not the limit of the function. So you are correct, there's a limit of 0 there. But when you use this limit, it doesn't work. So you see in this calculation, I'm using that formula, that different version of the formula to calculate a limit. Okay. So coming from the left, -1, coming from the right, +1. No limit for that function, for that equation, not necessarily for the function. So this is what we're getting to. If a function is differentiable at C, then it's continuous. What did we just illustrate with the absolute value? We illustrated that the opposite is not necessarily true. Just because a function is continuous doesn't make it differentiable. However, if it's differentiable, it must be continuous. Does that make sense? Okay, it works one way, but not the other way. And hopefully when you get to that point, you remember that absolute value version so you can recall which one works and which one doesn't. If it's differentiable, it must be continuous. So in red, differentiability implies continuity. The reverse is not true. Continuity does not imply differentiability, which is what I just said. Okay, good. It's not day 20, is it? It's day 18.
Yeah.
My slide shows up. Okay, a lot of information today. I understand that. Comparing the two things of the mechanics and the concept, for today, the concept is more important than the mechanics. I think by now you can all take a limit and you can plug and chug into that difference quotient. But it's important that you understand where we're going with this, because it'll make the transition for the upcoming lessons quite a bit easier. Okay? Questions, concerns, anything for the good of the cause? Outstanding. I'll throw your test scores online later today.